When capacitors are connected in series, like in this setup here, the voltage in the circuit is going to be distributed as shown through this color code. For example, the brown here tells us that the voltage all over here is the same. And that's because we have just a conducting plate of a capacitor connected to the end of the battery by a conductor. Remember, whenever we have a conductor, the electrical potential throughout the conductor is the same. That's why it's all brown. Similarly, we have a plate of a capacitor connected to another plate of another capacitor with a conductor, so that's why we should have the same electrical potential, and it is shown in blue here, since it's going to be different than the electrical potential here. And last, this capacitor plate is connected to the positive lead of the battery, so they are at the same electrical potential. Now, when we connect the circuit, when we make the circuit connection, negative charges from the negative of the battery are going to flow towards this end of the capacitor. At this end of the capacitor, because of the proximity, because of the distance separating of the plates is small, these negative charges, once they arrive here, they are going to push the negative charges here away. Where is it going to push them to? The furthest away possible. That would be here. So whatever negative charges here are going to be pushed by these negative charges. And I'm going to have a buildup of negative charges here. These negative charges, in turn, are going to push the negative charges that were here away. And where are they going to go? The furthest away, and that would be to the positive lead of the battery. So the battery loses negative charges from here and gets negative charges from here, and that allows it to complete the necessary chemical reactions to produce the electropotential between the two ends of the battery. Now, focusing on the charges. This end here that's shown with a dashed line is insulated from anything else. It's insulated from the battery. There is a gap here and another gap here. Because of that, the total amount of charge here is going to remain zero. It's not going to change. It's going to be distributed such that I'm going to have a buildup of negatives here and a buildup of positive charges here, but the overall charge is going to remain zero. We didn't have any charge coming in or out of that segment. Now, in each of the capacitors, the relationship for capacitance tells us that the charge is going to be given by this, Q1, C1, delta V1, where delta V1 would be the voltage difference between these two ends of the capacitor. And Q2 is C2 delta V2, where delta V2 is the potential difference between these two leads. Since the total charge here is zero, that tells me that the charge here is the same as the charge here. But for a capacitor, the charges in each lead are the same, except opposite sign. So if I have minus Q here, I should have plus Q here. If I have plus Q here, I should have minus Q here. So that tells me Q1 is equal to Q2. Let's call it Q. The two charges in the capacitors are going to be the same. The voltage across them are going to be different. Delta V1 is going to be Q over C1, delta V2 is going to be Q over C2. So let's focus on the voltages. Delta V, that's the voltage from here to here. That's the same as the voltage from here to here, plus the voltage from here to here. As an example, if you need an example, let's say if I have a voltage here of 0, and here let's say it's 12 volts, and let's say I have 9 volts here. So the voltage from here to here is 12 volts. The voltage from here to here from 0 to 9. And the voltage from here to here is 9 to 12, 3 volts. Overall delta V is equal to delta V1 plus delta V2. Again, delta V1 is Q1 over C, delta V2 is Q2 over C2, but since Q1 is equal to Q2, we can write it up like this. If we were to replace these two capacitors by an equivalent capacitor, and having a circuit that's going to look like this, with just one capacitor replacing these two, that we call, whose capacitance we call C equivalent. So we are going to have the same voltage across the battery, and we should have the same amount of charge stored in the equivalent capacitor, Q. So delta V, the overall voltage drop, is going to be Q over C equivalent. So if we write that out, delta V is equal to Q over C1 plus Q over C2, and it is equal to Q over C equivalent. Simplifying by Q all over, so we get 1 over C equivalent, 1 over C1 plus 1 over C2. Okay, we can rewrite that as this. We did the analysis here for 2 capacitors. If we had 3 capacitors in series, all 3 of them are going to carry the same charge as well, and we can do the same analysis. 1 over C equivalent then would be 1 over C1 plus 1 over C2 plus 1 over C3, etc., no matter how many capacitors you place in series.